published more than 50 reputed high indexed high impact factor journals, more than 50, as well as he secured 768 citations, as well as H index is 60. So very good achievements in academic also. He got gold medalist in UG as well as PG, her academic side, as well as research background. Also, uh, he got many awards and achievements. Uh, now,
Thank you, Gopalakrishnan
uh,
sir. Very
yeah,
kind of you to
uh,
introduce me. So now let me introduce Professor Abhishek. I'm really honored to chair Professor Abhishek's session. I know him from my PhD time. It's almost a decade. And Professor Abhishek, he obtained his PhD from Tohoku University in the year 2004, and then he's a postdoctoral fellow in Tohoku University as well as Rice University and UC Santa Barbara. And he's involved in diverse fields, including machine learning, 2D materials, thermoelectrics, catalysis, optical materials, topological materials, and defects using density function based approaches. So, in the field of machine learning, Professor Abhishek's group focuses on development of advanced materials database and building ML machine learning based models for accurate prediction of specific properties. Each group has established India's first computational materials database, ANAND, which consists of electronic and structural properties of about 25,000 maxines. And this database is currently the world's largest database on 2D materials. And also, his group focuses on 2D materials such as graphene, metallic sheets, maxines, heterostructures, metallic structures, clusters, and nanowires. And phenomena such as semiconductor to metallic transition, optical vibrational properties occurring due to the application of pressure strain on these 2D materials are being studied. And currently, he is involved he's actively working in thermoelectric materials, and also his group extensively studies on defect physics of various classes of low dimensional materials. And you can the end the list goes on because he has almost touched all the fields, and he has got many awards, out of which the prestigious awards like MSRI medal from MRS of Society of India in 2014, and he's a JSPS fellow and also next fellow, and he has published more than 160 papers, and he has got a very big research group, and his achievement is enormous in all these years. And with this, I ask Professor Abhishek to deliver his lecture on um, on the topic what he's going to talk. Thank you, Professor Abhishek.
Thank you very much, Surya, for your kind introduction. Okay, now I can share my screen. Thanks. Okay, you can see my presentation now, right? Okay. Okay, great. Okay, so first of all, let me thank all the organizers of this conference, especially Surya and Professor Kawazue for his kind invitation, and I'm honored to be here to present my work today. Although I'm not in Bangalore right now, I'm traveling, but this is an advantage of using Zoom, that you can give your talk from anywhere. Okay, so today I'm going to talk about ML-assisted discovery of novel materials with targeted properties. And please stop me if you have any questions, since the timing is 30 minutes. So I'll be a little fast. However, if something is not clear or if you want to have any detailed discussion, please stop me. Okay, so before I go ahead, I would like to acknowledge first the people who actually did the work. 1 second. Just let me take my laser pointer. Yeah, it's essentially my group members and also the funding agencies, which have been very liberal in funding us, including DST Nano Mission, DST Korea, KIST. And these are some of the computers which we have used to produce the data and the work which I'm going to show you. And most noticeably, Cray XC40 Sahasrat, Tej and Planck, which is our small cluster. We also very extensively use TUE CMS computational facility, which is hosted in SSU department. So, I mean, a couple of these slides many of you have seen before. So the aim of the machine learning is essentially to find out the patterns in the data. So you need a high quality data, and then you predict the pattern automatically, or extract the pattern from this data. And using this pattern, you can predict the future outcomes. One of the examples which you encounter, or all of us encounter when we go and check our email, that you'll see that there is a spam email box, and there is a ham, or you can call your actual email, which is inbox. So essentially all the emails gets very nicely, filtered out or classified into spam and inbox. And you can read the emails which you are really interested in your inbox, and ignore or delete your spam messages. And this gets better and better as and when you use more your mailer software. Other examples are all the uh, video hosting sites, including Netflix, and essentially mostly during the COVID time, the streaming platforms became very, very important. And there are way many more platforms today exist than a year back. And you must have noticed that in any of these platforms, when you go, they recommend based on your history. And many times these recommendations are very, very accurate. And most of the time you end up watching what they recommend you on your very first page, even though they host billions of the videos, which humanly impossible for us to browse through and select a video which we like to watch. And that's where, so you see this whole process of recommendation also involves something called as a decision making. So that's where the machine learning helps you. So it helps you based on the features or patterns in your viewing history to recommend something, or makes a decision for you. Okay, this is what you are most likely to watch. And similarly, same algorithms also works for the various shopping websites. So all of this became really, really popular. And uh, during the last 1 year, during the lockdown time, people started spending more time online, even for their day-to-day grocery shopping. And they got really helped by all these very powerful machine learning algorithms. Another one also is speech recognition, which is basically many smart speakers which exist in our households, and they can recognize our accent, the area where we come from. Even, for example, within the India, it has a different accent. People speak in different accents, different languages. And these speakers are very, very smart in finding out what we actually mean, even though we are not pronunciating some of the words very clearly. So this is another very powerful application of that. So another thing that these are some of the commercial uses which you see, but there are so much research. Any company, doesn't matter which sector you take it, whether it's finance, manufacturing, travel, any industry you go, they keep on analyzing the data. So if they don't have an analytic program, they are considered as a blind because they don't know where they are going. So machine learning, so the bottom line is that machine learning works for industry. What about materials? So this was about 10 years ago when people recognized that, yes, it can work for materials also. And this was the initiative started by President Obama, wherein he wanted to accelerate the process of discovery of materials to the device, which usually take 2 to 3 decades. So can we do it faster? And with, of course, any initiative which happens from the White House label automatically starts with a huge amount of funding in the orders of billions of dollars, and then that initiatives trickles through across the globe. So it went to US, Japan, Europe, China, India, Korea, everywhere. So all of the countries now are indeed actually working or having a very active program on Materials Genome Initiative. India was a little slow, but now it is picking up. I can very clearly see that. There's a lot of activity which have recently started in India also, even at the government level, wherein people have recognized that, yeah, machine learning can help them to accelerate or to search materials which have a novel properties. How does it, but so far now, it's already 10 years since this initiative started. So one can ask question, what did it give us so far? So one of the things, besides giving us various models, which I will tell you in a minute, But one very important tangible which came out from this are these databases. And starting with materials project, aflowlib, NIST, Jarvis, Kazana. So like CPDB, it has almost 1 billion molecules, databases of 1 billion molecules. Nomad, which came from Europe, has almost, I think it has already crossed 5 million data points. So there are so many databases which currently exist that if you are an experimentalist and you like to work on a material, there is a very high chance that that material's basic information about that material does exist in one of these databases. So it's very useful for you to go ahead and check and get some of the basic information which will help you whether this is the material you want to study or not before you invest some resources. So I find this as a very big and important tangible which this Materials Genome Initiative has brought to us. But the story doesn't stops here. It actually starts from here. So now what we can do with this data is what we have been doing. So when I started, that time literally there was nothing in India. And and I realized that even many of these databases which I'm showing you, they were also not there. Only Materials Project was there, aflowlib was there, and yet they were very big. So it was very difficult to compete with those databases. So you need, and I didn't want to compete. I actually wanted to contribute. So we came across with a kind of a material idea of a material which has a possibility of a huge amount of data points, and that was Maxine. And we created the database of the Maxine, which is called as Anant. It came in 2018. We released it to the public, and it has about 25,000 Maxines. I request all of you to please go ahead and have a look, give us suggestion, contribute, and use it. It has a computed data of about 25,000 Maxine, and it can tell you whether the structure of the material. Then you can download those structure in either CIF form or POSCA form. You can look at the band structure. You can it also tells you whether it's a direct band gap or indirect band gap. And there are many more other properties which you get from DFT calculations, and that we are going to release. But this is not going to be limited to just now. Now we are working on other classes of 2D materials, which is almost ready and can come out any given days. And so now Anant 2.0 is going to be released very soon. So wherein you will have some thermoelectric database data, and you'll have more 2D materials database. And if we resolve some copyright issue, we may release the structural materials data also. So we'll see. So please keep checking, and you'll find some updated informations here on the Anant website. I'm happy to share that in 2019, this review article came, and wherein Anant was featured on the global map of the database. Okay, so now when we have this data, what can we do? We basically try to build model or find these patterns. So these patterns are essentially a function or model, which we try to get from the data which we have. So we start with a large database, and then we calculate the true response function for a smaller part of this database. For example, let's say GW band gap. So I have a Maxine of 25,000, Maxine database, which has about 25,000 material. And then we want to develop a model. So what we'll do, we'll take about 100 of Maxine, calculate the GW band gap, which constitute this smaller part here. Then what will happen, we split it into two parts, like these are the input data, X, and the Y is a true band gap, which I know. Then I'm going to split this data into test and train. Generally, it is done in 90-10. So for both of this, I know the true answer. So I will train a model to my train data and then compare it with the true value. And if it is good, then we take this model and apply to the unseen data and check again the performance. And if the performance is satisfactory, we'll accept this model and apply to the entire database. So basically this GW band gap model, which we have developed, it can calculate the band gap of all the Maxines which are there in a matter of few seconds. So something which would have taken using Sahasrat nearly 20 years to calculate the GW band gap of all the 25,000 Maxine. Now using machine learning based model, you can quickly do it within few seconds. So this is the kind of acceleration which was in reason for these machine learning approach which now machine learning models are delivering. So some of the important factors which comes when you build a model, or wherein, like what is the, since where does a material scientist or physicist or chemist comes in? So our role comes in part of the feature selections, because we have our chemical intuitions, materials intuitions, or physics-based intuitions, which can help us to find out what are going to be our x. So since we are mapping a function f of x, right? So we need to know what could be our input data x. And therein we use our domain knowledge to work out what are those nice or easy features which can map uh, our data to a particular output or response function which we are looking at. So our group's philosophy is that we look for the features which are the most simplest and easy to get, because our ultimate customers are experimentalists. We want experimentalists to use this model and have confidence in these models, so that before they go to laboratory and synthesize the material, they have a very good understanding of especially the properties which they are interested in, or some good expectation of the properties which they are going to have. So these models should be very, should be easy enough for an experimentalist to use. So most of the features which we generate are based on the elemental properties of the elements involved in your compound, not even the compound's properties, because compound's properties sometimes you don't even have it because they don't exist actually many times. But all the elements exist and their basic informations also exist. So using that, we build the model. Okay, if you know the structure of your compound, that is added part. So then we can extract some of the information from there also. And sometimes, not always, a small VASP calculation or DFT calculation of a 5 minute is good enough to give us enough features to, to, to find out the Y value which we are looking at. So first thing which we did, our first model which we built was a semiconductor metal classification model. And here is the performance of this model. So it has an accuracy of 99%. So I'll just come directly to this plot, which is called receiver operating characteristic. This is one of my favorite example, which shows the power of machine learning. So what does a classification model do? It classifies whether a particular vaccine is a metal or semiconductor. So herein, suppose if I do this job by toss of a coin, so then I have a 50% chance of fail or pass. So that would be this 45-degree line. So there is always a 50% chance of getting a metal or semiconductor. So I'm not making any decision, right? And just it's a random thing. However, when I start using features, mostly elemental features about my compounds, and create a classification model, this line shifts towards a rectangle now, because area under the curve gives you the accuracy of this model and can reach all the way up to 0.99, so almost 1, right? More rectangular the shape is, the more accurate your model is. And this gives you a very highly accurate model to predict the semiconductor or metallic vaccines. So herein you can see that now we are taking a decision based on these 14 elemental information. This is what basically wherein the power of machine learning comes in. So rather than having this random approach of 50% failure and success, now we have 99% of success. So this is really, really strong. And this can, I'm trying to convince you why people or the world believe in machine learning, because it's not complete, it's not at all random, right? It's just based on or built on the statistical correlations which these features have with our response function. Okay, once you know the band gap part I already covered. So once you know whether a vaccine is a metal or semiconductor, the PBE or DFT within PBE or LDA always underestimates the band gap. Actually, it does a very poor job. So in order to correct it, you go to the many body perturbation theory like GW, which is a very, very expensive, computationally expensive method. And it's practically impossible to do it for a huge, larger data sets like Anand. So what we did here, we picked up about 150 of them. We calculated the GW band gap and built a model, and we were able to create a very good model with the accuracy of about 0.12, and R square was about 0.89. This was a bagging model. So we use various algorithms, of course, KRR, SVR, baggings, and GPR. And we found that GPR turns out to be the best approach to get a highly accurate model. We also looked, these are like a byproduct of actual model which we had. So herein what we get is also looked into the important features. Which one of the features played most important role in the prediction? So in this case, we found, for example, volume. And sometimes you can derive the underlying physics from these features. Why a certain features is having a more importance, and very many times you'll find that it aligns with your intuitions or what you have expected. In the interest of time, I'll not go into the details of it, but here is, okay, I mean, one example which I keep telling it, for example, volume. So if suppose you have a larger volume, a compound which has or a maxine which has a larger volume, naturally it will have a lower band gap. This is what we would expect because the bond lengths are longer and therefore the wavelength overlaps between the wave functions are smaller, lower, and therefore the splitting is lower, and eventually you'll get a smaller band gap, and vice versa if you have a smaller volume. And this is very nicely captured by our machine learning models also. So it's not, again, causality is not expected, but we do see some of this already, and machine learning is able to capture those very nicely. Okay, so after that, the next application we looked at is the band positions, which are also unfortunately not predicted accurately in DFT. And once again, we use GW to predict, get the accurate positions of the bands. And so these are the various applications of these positions of the band, in electronic devices, whether it's a ohmic contact versus Schottky contact, band offsets, whether you find a type 1 or type 2 type of interfaces, which has its own advantages for optoelectronic devices. Then when you are making the photovoltaic, also you need to know where all the different layers which you have, Zauer layer, electron transfer layer, or hole transfer layer, where their VBM and CBM lies in a universal scale. So once you know this information, you can predict, okay, this material is good for absorber layer, this material is good for the HTL or ETL. So these are very, very important information which one needs besides knowing the band gap, especially for a semiconductor. It also controls whether it's a good photocatalyst or where will be the defect transition levels. So I can't overemphasize the importance of this one parameter, actually two in this case, the positions of VBM and CBM at the absolute scale. What you get out of a simple VASP calculations are not correct, because these numbers have no value actually, because there's no reference to it. So you have to refer it to the vacuum label and then get the accurate positions of these VBM and CBM. So we developed the two model, one for VBM and CBM, and what we found that the VBM model was good enough to predict both VBM and CBM. So one model was powerful enough, actually both of them do both. So you pick up any of these models, they would be able to give you both the position of VBM and CBM. And not only that, if you know accurately the VBM and CBM, then you get band gap for free, because you just take a difference and you get the band gap. So this was a very very good model, and the accuracy of band gap which you calculate using the aligned VBM and CBM was very, very much comparable to the previous model which I showed you. Now, next thing which we can do with the data, we can do a high throughput based materials design. So how does it work? Is, as name suggests, you do calculation or you do experiments on a large amount of compounds, and then you start applying the filters in terms of their properties. So for example, if I'm looking for a high or low thermal conductivity materials, lattice part of thermal conductivity materials, the screening criteria which I will use, first of all, I have to see that these, because we took these data from the materials project, and many a time these data, okay, once again, there is two things on the, what's your question? Okay, sorry, I thought this is question for me. Okay, so one thing we did, we optimized, then next, since we were interested in lattice part of thermal conductivity, therefore we wanted to get only the insulators or semiconductors. So we filtered out all the metallic compounds. Then we also checked their dynamical stability. So we remove all the compounds which were dynamically unstable, and finally we calculated the kappa L for about 180 of them. And what we found about 11 ultra high thermal conductivity materials. So the conductivity was more than 200 watt per meter Kelvin, and 15 ultra low thermal conductivity material kappa L, which has a 1 watt, which has a thermal conductivity less than 1 watt per meter Kelvin. And several of these materials already exist. So this is, we verified and found out to be true, and many of them are yet to be discovered. Recently, what we saw, one paper, just one of these 15 compounds, there is a one PR Critical Review Materials full paper on this one compound, which was actually listed in these 15 compounds. But it's an expensive approach. You know, this took us more than 2 years worth of calculation. But what we got out of it is an access to very high quality data. And that gave us, and here the bottleneck was the calculation for kappa L. Kappa L or thermal conductivity calculations are quite expensive. It takes about a week or so to get a thermal conductivity calculation for one compound. So what we did, we used it, but this time for feature design, we used just the property map, because now we had several properties, access to several properties, so we can create a property map. And what we found that there was a correlation between the some of the properties to the kappa L. For example, omega, or the phonon, the maximum of the phonon frequency, which we call it omega max. So if this one is low, for example, here it's a 2.5, the thermal conductivity is also low. If this one is high, for example, here it goes to 25 terahertz, then see the thermal conductivity is very high. So there's almost one-to-one relationship between them, and which we can see here also. You see omega max versus kappa L, and there you can draw a straight line here. So there was a correlation between them. Next, Gunnaisen parameter is the only one which is calculated within quasi-harmonic. It's not something which captures enharmonicity directly, but for thermal conductivity, you need to know how enharmonic your crystal is. And that we can get some information by looking into the Gunnaisen parameter. So this is what we did. And here again, we found that if the spread of the Gunnaisen parameter is very high, thermal conductivity is low. If the spread is low, thermal conductivity, so it's the inverse relationship. But that was not sufficient because there were some more problems. So what we realized that if you do an integrated Gunnaisen parameter up to 3 terahertz, that has the best correlation with kappa L. And mass and volume are the two other features which have a well-defined reason why they have a certain relationship with the kappa L. So using these 4 parameters, we developed a model for the kappa L prediction, and look at that. It's one of the very beautiful model, very powerful, very low RMSE, very high R square, extremely low residual. And we compare it with a very popular SLAC model, and you see how bad the SLAC model performs. For almost everything, it overestimates the thermal conductivity. But if you look at the SLAC models, this is the final formula for kappa L in SLAC model, you'll find that some of the features which are used, or in this case, the variables or parameters which SLAC model uses, are very similar to what we have found. For example, mass, volume, gamma, and then, but the only difference is their interrelation, which here was kind of found through the highly sophisticated machine learning based algorithm. This was based on semi-empirical approach. So what if we use these features and build a machine learning model? And what we found that, okay, now it works very, very well. So it's this empirical or semi-empirical approach formula of SLAC have problem, but his descriptors are pretty good. And you could see that we get a model which is very, very good, not as good as what we found with our descriptors. So sometimes machine learning can help to improve some of the same empirical models which do exist. As you know, there are huge amount of approximation goes behind any semi-empirical model, and that can be corrected using machine learning. Now, another problem we looked, something which was not there until today, it's not there, at least physics-based model, wherein you can map or relate the electronic transport to thermal transport. when we talk about the thermal transport, we are talking about the lattice part of thermal transport, not the electronic. There is, of course, electronic part is related by Weidemann and Franz law. So, S and sigma, we get it from our electronic properties, and that is very, very easy to get. You do a band structure calculation and very quickly you can get this S and sigma. However, kappa L, as I told you, is very expensive property. So, and for a thermoelectric, where we need to know both the transport parameters quite, necessarily. Therefore, what we do, it would be good if we can somehow correlate our electronic transport to thermal transport, and then we have an idea which one would be a better thermoelectric material. So we first build a model for the S, which is a Z-Vec coefficient for both N and P model. N and P type of semiconductors, and you see that the models were very, very good. Then we develop a model for sigma, which is for the conductivity. Here again, we got a very good model. You may ask, why are you doing that? Okay, one is that we are getting a very good machine learning model. Of course, it is very easy also to get it directly using Boltzmann transport equations. However, what we wanted to look for is the features. What are the features which control these? And then we already have a model for the thermal conductivity. And then what we will look, which are the common features, the features which cross cuts in both electronic transport as well as thermal transport. And this is what we did, or we call them a bridging descriptors. And they were very simple, like bond distance, bond strength, volume, electronegativity, coordination number. And you see that they are all kind of correlated and they do make sense. For example, bond distance, right? So something, if it has a smaller bond, will have a more dispersive band. That means its electronic transport will be governed by that, right? And similarly, if bond distances are smaller, that means the force constants are going to be stronger or more harmonic. And if you have a more harmonic, the thermal conductivity will be high. So the one simple descriptor, bond distance, does have a correlation both with the electronic transport as well as lattice part of thermal transport. And therefore, these are good bridging features, which comes out automatically when you create these independent models. So we picked up these bridging features and added S and sigma in addition to that, and created a model for the kappa L. And look at that, how nice these models are. The R square is about 99%, and RMSE is as low as 0.19. And see that everything is all the data falls within the 2%. So residual is also very low. So this was probably the first time where we have connected something which is completely unconnected. So electronic transport and thermal transport, which are not connected, can be connected by using machine learning. Of course, learning from machines. So here what we found that bond distance and sigma, for example, if you know these two, very easily you can tell which of them will have a lower thermal conductivity and what kind of compounds will have a higher thermal conductivity. We also looked at the transferable models. When I say transferable, it means like most of the time when people develop the model, it is developed for a one class of a material. So if you use the same model, suppose the model I have developed for MXene, now if you like to use it for silicon or 2,6 semiconductors, it may not work. And it is not supposed to work also, because it was developed only for the particular phase space, wherein or feature space, I would say, for a particular type of elements or structure or chemical space. And there it works very well. But the moment we take something out of it, it will not work. So that remains a problem. So basically for every class, you have to generate a newer model. So one way of doing it, you make your database, which is should have as much variability as possible. So for example, we extended our database and created a new database wherein we have all the crystal system from 1 to 7, mass varies from 8 to 193. So these are my feature spaces. Volume can go all the way from 40 to 625, and the thermal conductivity varies by almost 4 or 5 orders of magnitude. So this has a huge amount of variability. And we created a model, yet it was okay model, but not very good model. Okay, so how do we get? So we created what we call a Kriging approach, wherein we develop the local models for different classes of material. with a condition that the models are continuous at these boundaries, right? So if a model I created for the blue part and the green part, they both should give me almost similar answers for the elements or for the data points which lie in this boundary region. So that is the condition which you apply and then develop a model. So these models, so these individual models are going to be very, very accurate and highly powerful, much more than the global model which you have. However, now it is, we have a set of models which does a job rather than one single model. And this is also known as a patchwork rigging. So we applied that, but with a slight difference that we partition our data. Now you have to partition that data. So there it was easy. It was done through the color. But in this case, we partition this data with respect to the kappa L or thermal conductivity itself. We tried with various other features, but the best partition we got with the kappa L. Now we need to know kappa L before we can even predict. So for knowing kappa L, we use our global model. Okay, so first we use our global model, which will guide the point either to this partition or to this partition. And once our data point gets partitioned, guided to either one of these partition, and then it gets another model takes over and predicts the thermal conductivity. And that's why we call it a guided patchwork rigging. So this is the algorithm also which was developed in our group. So this was the performance of the localized model. You see, they have a RMSE of 0.13 as opposed to 0.25, which we were getting from the global model. So using the combination of these two, or through the guided patchwork rigging way, we were able to develop a model which has a more wider range of applicability with a much more improved accuracy labels than what you would get with a global model. So we tested this model to 10 unseen compounds like this. So our global model was was able to send them to right partition very, very nicely. So here's an example. And then these two guys, the model for partition 1 and partition 2 did a very good job of predicting their thermal conductivity. Okay, now in the end, I'll talk a little bit about structural materials wherein we have started working. And there what we do, we take the microstructures or the SEM images. From there, we generate the features. And then we use some either geometrical features like looking at the area, perimeter, etc., or statistical correlation among the pixels as our features, and add some of the processing information or elemental information to build the model to get, for example, Young's modulus, yield strength, or I mean, whatever mechanical properties which you are interested in. So structural materials are basically alloys or superalloys, and the type of material, the properties which are most important for them, as names suggest, are mechanical properties. We predict their mechanical properties by just looking at their microstructure. And so we started with about 110 microstructures. We use some filters to make it, we denoise these structure, then we binarize it. Okay, so this is for us nickel-based superalloys. So here you have a well-defined gamma and gamma prime phases, and after binarization, everything comes between, every pixel will have either 0 or 1 value. So we have to put a threshold to do this job. And then what we do, we use connected components to get these geometries around it. And once we have these white area in certain geometrical arrangements, black area in certain geometrical arrangements, and then we go on and calculate the effective area, effective perimeters, effective radius, etc. Then we use microstructural, elemental, compositional, and processing parameters as our features, apply the lasso to reduce it, which reduces it to just 9 relevant features, and you develop a model for, in this case, we have developed for a Vickers hardness, and you see how nicely it works. So it gives you the RMSE within 0.13 to 0.15 and very high R square of almost 99%. Second approach, which was a 2-point correlation based approach. So we have these binarized image, then we have a gamma gamma correlation, gamma gamma prime correlation, and gamma prime correlation. And but any one of them is good enough to do that. So what we do, we take a white here, white pixel here, then we try to find out the probability of getting the another black pixel in the entire image. So the size of the this chart which you see is depending on the size of your image, and this can run, in this case it's a 40,000, but if you have a very high resolution images, it can go to the millions. So there the number of features are suddenly very large. We obviously cannot work with such a large number of features. So what we do, we use PCA, or principal component analysis, which actually tells you, is essentially a coordinate transformation, and tells you the coordinate directions which has the maximum variability. So for example, this was the x1, x2. For example, you rotate it, go put your axis now in this direction. So you see the PC1 covers most of the variation, and PC2, whatever left is a little bit, is along the PC2. So two principal components were good enough to capture most of the variability in the data. So this is what we found in our data also. Of course, in our case, we needed almost about 25 PCs to capture almost 80% of the variance. So we stop at that point. Of course, we cannot, as I told you, there could be PCs are same as the number of pixels. So in this case, it was 40,000. However, only 80 were good enough to capture the variance. So we picked up these 80, and on top of that, we apply the lasso to reduce it further. And then we add compositional feature and PC feature, just two types of features, and see we get a very strong and very nice model about 0.11, 0.12 RMSE, and 99% was R square. We find some of the correlation which was known in the metallurgy community. For example, iron has a positive correlation with the hardness if you add iron, and aluminum has a negative correlation with the hardness, and this fact is known to metallurgists. So some of these things, as I told you, always we do not expect a causality, but many times machine learning, we can learn from machine also, which was true in this case also. So in conclusion, I showed you what are the different type of things we do. We create models for electronic properties, thermal properties, and even the structural properties. We also try to find the hidden connections between the physical properties. For example, in this case, the transport, the electronic transport and lattice thermal conductivity, which have almost similar origin, but there was no connection, which of course machine learning can help us to do that. And also we developed some of the algorithm to develop the model which has a more wider applicability. With this, I think I'll stop, and I thank you all again for your kind attention, and I would be more than happy to answer your questions.
Thank you, Professor Abhishek. This was very nice and wonderful talk. And there are a couple of questions from Dr. Abhijit Chatterjee. And first question is, how many other parameters you have seen to influence the band gap?
Yeah, okay. So there were many. So we started with 54 parameters, okay, and eventually, so if, for example, for the classification model, we just use 14 elemental, and that was enough. Herein, we started with 54 parameters, but we got about 15 were good enough to predict the band gap.
Okay, the other question is, do you have any specific recommendation with the algorithm, with, if any, for inorganic materials?
There is no such recipe, honestly. It really depends on the amount of data you have. If you have a high quality data and good amount of data, actually, so there are two approach, right? I do not have time to go into it. So one is frequentist approach, which is, like KRR, SVR. Other one is a Bayesian approach, which is this Gaussian process regression. So what my experience tells that if you have a smaller set of, if your data set is smaller, then Gaussian process regression or Bayesian based models are very good. If you have a large amount of data, GPR will be good even for for those cases also, but it will become more computationally expensive. KRR, SVR will, or frequentist approach will start to work better. And if you have a very, very large amount of data, of course, then you use the neural network. Yeah.
And Professor Das, he has a question for you.
Yeah.
Sure.
Hello, Abhishek. It was
Yes.
a marvelous talk. I enjoyed it as usual. Okay. I have one question, and that is in connection with the band alignment in semiconductor heterostructures that you mentioned. Okay. Hello.
Yeah, please go ahead,
Yeah,
Professor Das. What is your question?
My question was that, when you do that band alignment in either 3.5 or 2.6 semiconductors, then from the DFT studies, when you give your training set, then do you do it for the VBM as well as for the CBM? Because the CBM does not come out correct from a standard DFT, right? So do
Very,
you do
very
only
good
for the
question.
VBM or both for VBM and CBM?
Okay, thank you very much, Professor Das, for a very nice question. That's how I used to also think, that VBM is the only one which is the correctly come out from the DFT. Okay, but what we found, as the moment you start using LDA or GGA, even the VBM are not correct. And then you need to really align VBM, and then of course CBM also. And we did it again using GW. So the VBM and CBM which we have got or we have used in our data set are again calculated from the GW.
I see. Okay. And
so that's an excellent point actually. And the difference comes because of the screening effect. Why the charges on, the VBM, why VBM are not where it should be, is mostly due to, the screening is not good.
Okay, good. The other small clarification that I wanted is that how about the deformation potential? Because there is a huge interest. There is a huge interest, as you know, for the pressure effect, the effect of the hydrostatic pressure. So, is there any attempt either by you or by somebody else on the on the estimation of the deformation potential for the semiconductors? Is there?
Oh, this is another very, very good question, Professor Das. So we have done, and unfortunately, I did not show it today. Okay, so one second. So do I have time? I can quickly.
Yeah. Because Professor Kawaso has also one question.
Do I have a time or?
Yes, sir. Please carry on.
I do. Okay. So Professor Das, recently we developed a model to calculate the relaxation time. And therein what we did, we have used, of course, deformation potential approach as well as, machine learning based approach. And what we have found that deformation potential approach is not that bad. It's very, very good in capturing the electron phonon interaction. And so that was very, not surprising, but I was very happy to see that. Unlike Slack model, which completely fails. Hello.
I'll discuss this maybe in a slightly more details later on with you.
Yeah, sure. But this was since I did not have time, so I could not show you that model. That is wherein we have looked at the deformation potential model also, which most of the time work much better than what we have seen what happens to our Slack model.
Thank you very much.
Okay, Abhishek, how many accesses to your database? What I'm asking you, for example, Kazaya-san published a paper for Maxim functionalized, and immediately in short time, experimenters made the experiment. And I want to let your database more famous, so maybe it is better to open something to experimentalists to be interested. And then in 2 years, you construct a database, and maybe in your future, if they access to your data and really conduct experiment and prove what you have predicted, and then your name will become much higher.
Thank you very much. It's a very nice question, and your suggestion also. So I know there is a lot of access. Should I tell it here or not? Maybe I should tell, because what people, as you could notice, that Anant is still on HTTP. This community I trust, so I can share with you. It's not even on HTTPS, because we are struggling with ISC how to put it on HTTPS. So it's really very easy for you to download the entire database. If you are clever enough, you use some web scraper and you can use it and download, no problem. And I know that people do it very often. So but they do it and they can just go and publish without mentioning us. But they know that it is done by us. So that much we know. Anyway, it is developed for the community. I would prefer if they take it from through the legal or the proper way. But there is a loophole in our website, which I know people are exploiting, and they're downloading the entire data set using Web Scraper. But I can't stop them right now. But Anand 2.0 will be on HTTPS, and then maybe we'll not restrict anyone. Please feel free, take every data you want, but it will be accounted for. Is exactly what you have asked. Right now, I don't have an accounting how many people I have downloaded or used. But when they publish, I know that they have used our data sets. Like in Carnegie Mellon, this Venkat, he has published some work using our data. There's other groups are also using it, and they're asking more different type of data, not just the band gap and so some other information which we are trying to. So as you know, my human resources are not that great. So if I get good programmers or database people, maybe we'll have a much more improved databases base, and hopefully I'll do that. But just and COVID had put us on back foot basically, because all my students went home and difficult to keep
I
track of
have good
them.
friends. I have good friends, computer people
Yes,
in
yes, yes.
Japanese, especially Kyushu University.
Yeah.
They may help you from
Okay.
computer side. Computer
Okay.
technology is much advanced. Yeah, yes, I think.
Thank you.
Thank you.
Uh,
Thank you
okay,
Good
very
to
one
see
much.
we
you,
can take
Sensei.
one last question from Dr. Saeed. Uh,
Okay.
uh, one more dear.
Very good to see you, Sensei.
Hi, I cannot turn on
Hello,
my
Saeed.
camera
How
for
are
some
you?
reason. I don't know. I'm trying to. Yeah, it's unable. Anyway, great to see you, Abhishek. It was a pleasure to attend your talk, and I enjoyed your very nice and informative talk. I just have a very general question.
Yeah, sure.
You are an expert. I hope you can just provide some insight on that. So in all these machine learning approaches, as you just mentioned, we usually use some kind of descriptors, and mainly, they are applied to some kind of local orders in the system. And as long as they are like local orders, they tend to give very satisfactory outputs. But as soon as it comes to non-local orders, usually we see that it's not really that much helpful to use machine learning. And that's basically because we cannot find a proper descriptor to describe those non-local properties. And usually when it comes to quantum properties, you can find many non-local orders. Let's say the simplest is topology, but it's not the only one. You can go beyond that. So do you see any possible direction for finding proper descriptors that could be applied to those kind of non-local properties?
Very good question, and this is a question on our ongoing work. So we are trying to develop, and we are not the first, to be honest. There are people who have developed some models for the topological materials also to predict the topological phases. We are not going that far, but there I agree. When you have very complex, when your your response function becomes more complex, it becomes very difficult to find a simple descriptor to correlate it to your response function. However, if we approach that problem without divulging too much detail right now, because that will become a very long discussion. So our approach have been, going in a stepwise way. So suppose if we try to calculate a certain property, but we don't directly calculate that, we divide it, and divide and conquer approach we apply. So we go to something which we can predict accurately. We may not be able to predict the final thing which is there, and then using the machine learning combined with high throughput approach, we go and predict the actual y which we are interested in. So I'll tell you more details once we finish this project. So we are in the middle, so we don't know if it will work, but so far we are getting good response on that.
Perfect. Thank you so much.
So this is one of the approach we found that yes, you are absolutely right. We probably not we don't have enough domain knowledge to capture the right kind of descriptors to give us those complex quantum properties which you are hinting at. However, you know that quantum properties has various conditions, right? And we can build the model on those conditions. So we can pick up, let's say, the very simple example, because it's very trivial, like inversion symmetry breaking, or suppose somewhere the time reversal is broken. So all those things, maybe we can capture one by one, and then finally look for whatever type of quantum material you are looking at. So not final result is still, you may have to do your actual, the physics-based approach, but the steps can be can be found through machine learning. I'll send you once we have something on that. I'll privately share.
Yeah, and if time allows, I just have one more short question.
Sure.
Is it okay?
Dr. Said, can you have personal interaction, because we are already running out of time. We have 3 contributor lectures. I'm really sorry about this. Since you are good friends, I think you can talk later about this.
Okay.
Yeah,
Thank
thank
very
you.
much. Yeah.
Yeah, thank you, Professor Abhishek. So now it is time for the contributory lectures. So the first contributory lecture it will be by Xiao Yun Thion. So I request Thion to share his screen and start presenting. Yes, so you have to present for 8 minutes and 2 minutes for the questions.
Am I audible?
Yes.
Yeah. Okay, thank you. All right. Good evening, everyone. So my name is Tian. I'm from IIT Bombay. So I'm going to present to you my project entitled Photocatalytic Nitrate Reduction over Silver Modified Zinc Oxide. So a brief, quick introduction. So according to WHO in 2017, there are 2.1 billion people in the world who do not have access to clean water. And nitrate itself has been identified as one of the major pollutant in water, and it causes eutrophication. So out of which usually there are only 30 to 50% of the nitrogen in the fertilizer used by vegetation. And the problem with nitrate is it can be fatal, especially to infants under 6 months, something that is known as blue baby syndrome. And according to the Bureau of Indian Standards, the maximum residual limits of nitrate is 45 milligram per liter, which is also equivalent to 10 milligram per liter of nitrate nitrogen. So there are many different kind of technologies, existing technologies available, but here we are proposing using a photocatalyst where we can actually transform nitrate into something harmless, such as nitrogen gas. So what we are proposing here is a silver zinc oxide as the photocatalyst. So we would like to explore the capabilities of silver zinc oxide to reduce the nitrate in the presence of UV light. And secondly, we would also like to study the effect of various parameters on photocatalytic nitrate reduction. And so this is our experimental setup. As you can see here on the left side of my screen, this is the reactor, and then on the side there is this portable handheld UV lamp, and then there is this zinc oxide, silver zinc oxide, the FEG same image, and then which shows the presence of the zinc oxide, and then we have the XRD graph. If you can see here, they are colored box, which again affirm the presence of silver in our nanocomposite. So the first thing that we did is we try to study what are the factors which affect this nitrate removal. So from the graph that we can see here, sorry. Yeah, so from the graph here, we can see that it is very clear that photocatalytic nitrate removal only occur if we have UV light, if we have a photocatalyst in the presence of nitrate, and also formic acid as the whole scavenger. So in the absence of any one of these elements, photocatalytic catalytic nitrate removal will not happen. Then we go a little deeper. We study the effect of the silver content in the photocatalyst. So what we can see here is, let's look at the figure B. It is more clear, I guess. As we increase the silver content in the photocatalyst, there is a gradual increase. The red bar here, there's a gradual increase in the percentage of nitrate removal, but beyond 1%, which is 3% to 5%, the percentage of removal, it actually decreased. So silver, it acts as electron sink. So it actually trapped the electron, which enable a better charge separation. So that is why if we keep on increasing silver content initially, it also increase the percentage of nitrate removal. But beyond 1%, if we keep further increase the amount of silver in the photocatalyst, it so happened that the silver tend to form a cluster. So hence that cluster itself become a recombination center. So the optimal amount here is silver content of 1%. And then the next parameter is the initial nitrate concentration. So again, in this figure B here, so we can see if we keep on increasing the initial nitrate concentration from 20 milligram to 100 milligram per liter. So there is a gradual decrease in the percentage of removal. And so this can be rationalized on the basis that if we keep on increasing the amount of nitrate molecule in the solution, so it's kind of it will absorb more and more to the surface of the photocatalyst, but at the same time, the amount of photon which is reaching to the surface of our photocatalyst remain the same. So hence, increasing the concentration of nitrate will not, it's not helping, it's not increasing our percentage of removal. And next, what is the effect of initial formic acid concentration? So we can see here from 10 to 45 millimolar of formic acid concentration, it leads us to an increase, a gradual increase in the percentage of nitrate removal, but beyond 45 millimolar, it doesn't give us any significant improvement in terms of percentage of nitrate removal. So again, similarly, if we keep on increasing the formic acid concentration, so there will be a competition between the nitrate molecule and the formic acid to the surface of the photocatalyst. And so if we keep on increasing the concentration of formic acid, it's not going to give us any more increment in removal. Then the next parameter that we study is the effect of different stirring speed. So if you can see here from 100 RPM at lower stirring speed, and as we increase to 200 RPM, we observe an increase in the percentage of nitrate removal, but beyond that, again, it is reducing. So at a lower stirring speed, we observe there is a stagnation and there is a sedimentation of the photocatalyst, but it improves. So as we increase the stirring speed, so it improves the percentage of removal. But if we keep on increasing the stirring speed, then if we keep on increasing the stirring speed, it will not enhance the percentage of removal, because we did observe there is a vortex exists in the middle of the solution, in the colloid solution, but and it resulted in non-homogeneous non-homogeneity in the solution. Then the next parameter that we study is the effect of the silver zinc.
Tian, you have 2 more minutes.
Yes, the effect of silver zinc oxide loading in the remover. So again, similarly, if we increase the photocatalyst loading from 0.5 to 1 gram per liter, we can observe there's a increment in percentage of nitrate removal, but beyond 1 gram per liter, it doesn't give us any significant changes. So we can say that the 1 gram per liter is the optimal photocatalyst loading. So here it can be rationalized that if we keep on increasing silver zinc oxide, we also increase the photocatalytic side. So that is why we can observe the increment here. But if we keep on increasing this photocatalysts, if we keep on increasing this photocatalyst, so we won't be able to observe too much of a difference, because increasing this photocatalyst, it actually also increase the turbidity of the solution, which will reduce the penetration of the light. And finally, this is the last parameter that we study here. It is the effect of light intensity. So if we increase the light intensity, if you can see here, from 50 to 150 microwatts per square centimeter, so there is an increase in percentage of removal up to 60%, but beyond that, it is reducing at 200 microwatt per centimeter square. So too high, if you see here, too high of light intensity, it results in electrons hole recombination. So here, this is a representative graph of a time-dependent reaction of a time-dependent of nitrate photoreduction, and the byproducts and the intermediates which it forms. So as we can see, as nitrate is being reduced, so here the bottom line is nitrite. NO2 is being formed in the beginning of the reaction, but slowly after that it faded. While at the same time, ammonium is slowly accumulating towards the later stage of our experiment. So hence we propose this is what is happening. So this is our photocatalyst, and in the presence of UV light and this formic acid as a whole scavenger, so nitrate, NO3 is being reduced, photoreduced to nitrite. And then again, it forms N2 and ammonium. At the same time, the formic acid is being oxidized to form CO2 and slowly become H2. Yeah. So this is the summary of my whole presentation. So the activity of silver zinc oxide, it was optimal, which is we reach 60% of nitrate removal when the initial nitrate concentration was 20 milligram per liter. And then the composite, if and in the presence of 1% weight of silver, and also with an initial formic concentration of 45 millimolar, stirring speed at 200 RPM, and silver zinc oxide dosage of 1 gram per liter, and light intensity of 150 microwatt per square centimeter. So we find that nitrate is the intermediate, and then ammonium and N2 is the byproduct. So here, the presence of nitrate, again, it confirmed the main mechanism of nitrate removal was via the reduction of nitrate to nitrate and then to nitrogen gas. So I would like to acknowledge the following departments, and thank you. That's all.
Thank you, Tian. That was really wonderful talk. Now the session is open for questions. So participants, if you have any questions, you can ask Tian. So Tian, how you confirmed the presence of like 1% of Ag in the composite? How did you confirm it is 1%?
Oh, we did a ICP, yes, on that.
So you did not do any EDS when you take the same image to confirm the percentage of silver in
We
the
did,
composite?
sorry. Yeah, we did EDS when we did FEG SEM, but in order to get a more precise value of that, we did ICP AES as well.
Okay. So what is the novelty of this work? Whether this is the first time you are using this material for this work, or is it already reported, or are you doing any modifications?
Silver zinc oxide as a photocatalyst is not completely new, but it's relatively new. A lot of area has not been explored. So that is why we decided to do a detailed study, like studying different parameters has been studied, but we decided to go a little further through more and more experimental condition. So that is that is the highlight of this study actually.
So what do you mean by N2 selectivity? N2
Oh,
selectivity.
okay.
Yeah.
So it is actually, sorry, just allow me to share that with you again. N2 selectivity is actually a ratio, okay, according to this calculation.
Okay. Okay. I
Yeah,
understand.
yeah. So this is N2
That's
selectivity is,
fantastic.
yeah.
Okay. Very nice. Thank you, Tian.
Yeah,
Thank
thank
you.
you.
So now I request Ms. Shanu to share her screen and start her presentation.
Okay, ma'am.
Yeah.
I hope you guys can see the screen.
Yes, wonderful. Yeah. Go on.
Good evening. First of all, I would like to thank the organizing committee for providing me opportunity of oral presentation with such fine lectures. And today I will talk about multiple carbon nanotubes grown over iron nanocatalyst for an electrode for hydrogen producing electrochemical cell. So this will be the roadmap of my presentation and why the hydrogen is important. So with increasing demand of energy in our society, the community has provoked to such an intensive research for the sustainable renewable source of energy. For the quest of competing with the fossil fuel, it's pretty required the catalyst, which is actually the electrocatalyst here, should be a catalyst which have the high reaction rate and the low over potential. Up to date, we know the platinum is a best catalyst for the hydrogen evolution reaction because its catalytic active sites are providing the HER with a near zero over potential. But the thing is that platinum is very earth scarce, and also its skyrocketing price is hindering its uses for the commercial application. So there is a quest to find an earth abundant material which is inexpensive along with improved catalytic performance. So for this purpose, we have synthesized iron nanoparticle used by two different routes, the green route and the chemical route, and use this iron nanoparticle for synthesis of MWCNT. And by this MWCNT, we are showing the hydrogen evolution reaction, and we also use this MWCNT in indigenously designed electrochemical cell for hydrogen production and collection. So as I stated that I have synthesized iron nanoparticle by two different routes. The first one is the green route on the left of the screen, and the right one is the chemical route. For the green route, we have choose the green tea leaf extract as a natural reducing agent to synthesize the iron nanoparticle and the precursor here is the iron sulfate. And in the chemical route, we have choose the typical sodium bordiohydrate solution for reduction of ferrous sulfate. And the figure 1N and 1B, you can see the typical excited pattern of both synthesized iron nanoparticle, which is having a peak around 45 degrees, which confirms the formation of zero valent iron nanoparticle. But in the case of green route, you see a peak, broader peak around 20 to 30, which is actually denoting the amorphous nature of synthesized iron nanoparticle. After this, synthesis of CNT using green tea synthesized iron nanoparticle was yet not discovered. So we have synthesized MWCNT via the CVD method, choosing these two catalysts as a precursor, and we try to maintain the rest of the experimental parameter constant. And here we have the same carrier gas, the same carbon source, and the synthesis procedure is followed by the carbonization and the purification process. And these are the ICONN image of synthesized MWCNT after we remove it from the CVD. And after the synthesis, we have characterized our sample through the scanning electron microscope and Raman spectra. The figure 2A on the left, you can see the SM image of MWCNT synthesized by the green route iron nanocatalyst, and the right one here is for the chemical route synthesized iron nanocatalyst with the magnification scale of 400 nanometer. As you see, these MWCNT possess a rougher surface with bundle of tangled tubes. And this rougher surface and the broken tubes due to the chemical treatment, the harsh chemical treatment. And also there is no trace of amorphous carbon you can see in same image of both CNTs. After this, we have took the Raman spectra of these CNTs, and we have see the characteristic peak of CNT in the both cases. In the figure 3A and 3B, you are seeing the Raman spectra of the CNTs where the D band is arising on 1390 centimeter inverse, which is correspond to the defects of the CNT, or you can say the defects of the graphene sheet. While the G band, which is coming around the 1600 centimeter inverse, is corresponding to sp2 hybridized vibration of carbon atom. The ID by Ig ratio we have calculated by the Lorentz fitting is coming around 0.9 for the green route synthesized MWCNT, and for the chemical route is coming around 1.5. As you can see from the graph also, the G intensity in the green tea synthesized iron nanoparticle is higher than this one. And here we see a less intense but broad peak at around 27 centimeter inverse, which correspond to G-res band, and it is actually a long range order crystallinity. Generally shows, the long range order of crystallinity in CNT. After the characterization, for the check of its electrocatalytic activity, we have performed the HER measurement in 3 electrode cell configuration using 0.5 molar H2SO4 electrolyte for the system, and the figure 4 and figure 5. Here figure 4 is corresponding for the GT MWCNT, and figure 5 is corresponding the MWCNT by the chemical route. And the A's of both figure, you see, we have coated our MWCNT on a conducting carbon paper of 1 cross 1 centimeter square area. And the linear sweep voltammetric curve is suggesting that bare carbon paper has no activity towards the HER, while the MWCNT is having pretty higher current density for the purpose. And the thing is that for any catalyst, if we are saying that it's a good HER catalyst, it's pretty important to it possesses the lower TEFL slope. So we have fitted this polarization equation using the TEFL equation, which is eta equals to B log J plus A. It's a well-known equation, and we have performed we have plotted the TEFL slope at different scan rate for both the catalysts, and we are obtaining a lower TEFL value of 98 millivolt per decade for the MWCNT GT and 91 millivolt per decade for MWCNT by the chemical route. And this lower TEFL value is coming due to the oxygen functionality and the defects we are getting here. And for a catalyst, it's also pretty important that it possesses the high long range order of stability. So here we have performed the stability cycle of 2000 cycle for both the catalysts and plotted.
No, you have 1 more minute, so you can.
Okay. We have plotted for the 2000 cycle. So there is negligible current density variation in the both. After the 3 cell measurement, we have seen good performance. So we have also designed an indigenous electrochemical cell, and on the cathode chamber we have used MWCNT coated conducting carbon paper of area 4 centimeters square as a working electrode here. And for the cathode anodic chamber, we have used the bare carbon paper, and for the separator, we have used the PVS3PO4 membrane and produce hydrogen production, the hydrogen and collected the hydrogen by a downward displacement method. And this is the image of the full setup that we have designed. And also we have plotted the amount of hydrogen produced by using both the CNTs in time span of 30 minutes, and plotted curve for different voltage. And this one is basically we have optimized the our coating, and this is on 10 milligram coating of the electrode. So after this, we have checked the presence of hydrogen using the POP test. And let me play the video. And this is quacky pop. And this is quacky pop sounds confirm the presence of hydrogen. So this is our initial result. On hydrogen producing electrochemical cell using MWCNT. So we are what we are focusing here. We are focusing actually bulk synthesis of CNT with better performance. So we can actually cannot. I won't say that we can replace the platinum, but we can come quite closer to the platinum value. And finally, I would like to acknowledge all the funding agency, my institute, IIT BHU, my supervisor, and all my lab mates, because their efforts is pretty important. And thank you everyone for your kind attention. Thank you.
Thank you, Sanu. So there is a question from the audience. So he's asking the graph between 2 theta and intensity, the XRD graph, how did you confirm the formation of the peaks? Can you explain that?
Yes, ma'am. Actually, iron nanoparticle from the literature, we know that they have a peak at 45. So peak at 45 we are seeing here. And I also plotted a glass slide peak here, because the amorphous nature is, when you have a amorphous nature, the peak of the size of the particle, iron nanoparticle, is quite low. So in literature, we have seen that actually I have to show some image for that. So the presentation was quite having only 8-minute time. So I haven't set it here. So we can see from the sample the particle size is quite low. That's why we are having an amorphous nature. This broad peak is coming, and but still it have the 45 peak, which confirms the formation of zero valent iron nanoparticle.
Okay, thank you. So, and what you recommend, whether it is green route or chemical route for this application?
Actually, what I'm look, what we are focusing here, why the green route instead of using the chemical route, green route synthesized iron nanoparticle is having 91 or 98. There's not much more difference that you can see in the TEFL slope. So yes, I'll prefer that people should use the green method to synthesize iron nanoparticle, because the chemical synthesized iron is highly unstable and you can't have it for the long time, while if you synthesize by the green method, you can have it for months or years, and you can synthesize TNT anytime. You have no bondation with that.
Okay. Okay. Thank you, Sonu. Thank you.
Thank you.
First, Gaurav Pratap to share his screen. Yeah, you can start.
Hello, am I
Yeah, you can
audible?
start. Yes, you can start.
Yeah, good evening, everyone. My name is Gaurav Pratap Singh, and I am PhD student at IIT Bombay, and I'm working with Professor Sobha Subha. And today my presentation topic is head-to-atom dope carbon quantum dot modified MOS2 composite applications in environment heavy metal sensing. So the objective of this work is to detect the heavy metal ion present in the water. So why do we need that? As we can see in this graph, the metal industries are increasing day by day. So the waste coming out of those industries are contaminating the water content. So there are many uh, hello. There are many metal based, for example, lead, nickel, iron, and these are very carcinogenic and uh, not good for health. So these are very toxic, so we need to remove that. So first we need to detect those metals, and then we can purify the water. So we are following this carbon dot method to sense the heavy metal ions. So why
So
carbon
can you
dot
go to the results directly? Yeah, that
yeah
will be very good. Yeah.
yeah hello
Yeah. Can you go to the results directly? You can explain more there.
yeah, like this, should I skip
Yeah,
those things?
yeah. It's fine. So this you have to explain this. You can explain. Yeah.
Like okay, so first of all we need to synthesize carbon quantum dot. So there are two different kind of approaches. One is top down and second is bottom up. So in top down approaches we just, for example, ball milling, and we, so in this case what happens, we do not get a good surface of the quantum dot. So we follow the bottom up approach. So in those there are several hydrothermal, microwave, and ultrasonic. So basically we have followed microwave method to synthesize our uh, carbon quantum dot. So there are applications you can see. There are several applications of the carbon quantum dot in bio, in optoelectronics, and also sensing. So here now come to the second part of the picture is MOS2 nanoparticle. So why MOS2? As I have found in literature that MOS2 nanoparticles are very good catalyst active, and they shows very good physical properties, and they have also large active surface area which is good for sensing application, and they also have high absorption capacity. So here in this picture you can see we use powder, MOS2 powder, which is bulk seeds, so which is highly dispersed in water. So there are several application of MOS2 in, for example, in sensing case. This is mostly used in gas sensing, chemical sensing. So what we are trying to use in water sensing case, and there are different process for synthesize the MOS2. So this is the one uh, literature I have found. So what they did, they just atta- uh, attach the carbon quantum dot on the surface of MOS2. Then they used for biocells. So our approach is uh, that we are using waste material. One is dye, which dye, and second is onion extractive peel, which is coming out of daily waste, right? So what will happen next? So we are taking those waste material and doing the carbonization. So basically in both cases, these are the nitrogen and sulfur is present in both cases. So we are getting nitrogen sulfur doped carbon quantum dot. So after synthesizing, we are going to use for heavy metal ion sensing. So this is the synthesis route we are following. We are using citric acid, which is a very good catalytic, and also it produces good carbon dots. So here we take carbon juice and methylene blue directly put into the oven, and then finally we get the securities. So here we have optimized the security. So what we did, we have taken the reaction time, varied the reaction time from 2 to 40 minutes, and also we have checked the excitation from 340 and 420. One is in visual and second in IR, visible, UV and visual. So we have found that in case of methylene blue, we are getting higher intensity. On the basis of that, the in this case the 30-minute one is showing better result, and also in onion.
Gaurav, you have got 1 more minute, so we
Yes,
have to rush. Yeah.
thank you. So this is the SEM and TEM image which confirm the presence of the uh, doped NS2 on the MOS2 sheet. And here in that TAM image, we can see there is a carbon deposit on the MOS2 sheet. So here is the FTI and Raman spectra, which shows the fingerprints of the our synthesis securities. And here is our application, which is PL based. So here you can see in this methylene blue derived NS security shows better detection for this iron. Here you can see iron and mercury and so on. So similarly, in this case also onion derived carbon dot, we are getting good result for iron and mercury. So now we have loaded the carbon dot on the MOS2. So this is also showing the good result for iron, mercury, and tin also. So this is based on this. This is our conclusion that um, nitrogen sulfur doped CQD shows better result as compared to simple security. And also the synthesized carbon quantum dot we have found from SEM and TEM, this is uniformly deposit on the surface of MOS2. And we have found the metal ions detection is good for iron and tin and for 10 nanomolar ratios. And thank you.
Yeah, thank you, Gaurav. We can have discussion later because the other session people they are waiting, and since this is a concluding session of ACCMS, I like to thank all the speakers and chair and the participants to make all the sessions a grand success. And we hope to meet you in the coming ICON conferences and ACCMS meetings. Thank you so much. Thank you so much.
Thank you.
Thank you, madam. Thank you.
Thank you.
Thank you,
Bye-bye.
Surya ma'am.
Thank you, madam. Thank you.
Thank you, Gopal sir.
Thank you, madam. Madam, close பண்ணிட
Yeah, because the other session is going to start. So in that case, we can leave this session.
Okay, madam.
See you again.
See you soon.
You're not coming.
Good evening, everybody. So this is session 5C. It's the themeless nanocomposites and catalyst and environment nanotechnology. So in this session, we have one invited lecture and 3 contributed lecture. This session will be hosted by Dr. Balachandra Kakare. So he is a associate professor from the Department of Chemistry. He's from Research Institute. So I'll give a short introduction. So his research interests are novel metal electrocatalyst. He works on novel metal free electrocatalysis, material electrochemistry, and to his credit, he has many projects funded from various funding agencies like EST and Titan Punish, and he has citation of 1844 and HMH of 22. And he is a recipient of many awards, which is mentioned here. With this short introduction, I request Dr. Balachandra Kakri to take over the session. Please, sir.
Thank you, Dr. Nisham. So we have a C5U session where we have one invited talk by Professor Rui Wurshalmi and followed by 3 contributor lectures. So we start with this invited lecture number 39 by Professor Rui Wurshalmi from the Hebrew University of Jerusalem, Israel. So Professor Rui is expert in designing and synthesis of hybrid nanostructures for photocatalysis, sensing, optical applications, and energy harvesting. He's also expert in developing new surface chemistries, synthesis, and surface modification of hybrid nanostructures, excited doping of nanostructures, and nanostructures array assembly. He has several awards and fellowships in his credit. For example, the Krill Prize, Kennedy Prize, and Career Development Award by Human Frontier Science Program. ERC Young Scientist Research Grant was awarded to Professor Rui for the development of the large-scale architectures with the nanometric structures interface for charge separation, transport, and interception. And he's a young fellow of Israeli Young Academy, a newly formed organization for the advancement of young scientists and science in Israel, formed by Israel Academy of Science and Humanities. With this brief introduction, I invite Professor Rui Wurshalmi for giving his presentation.
Thank you very much for this kind introduction and kind invitation. I will just share my screen. Okay, I hope you can all see the presentation now. So in my talk, I will describe our activities in the field of atomic and molecular layer deposition with an emphasis on material design by molecular and atomic layer deposition, specifically for photocatalysis. However, our activities in the field pertain to organic, inorganic, hybrid films in general. Photocatalysis is an example, conductive magnetic phase of oxides, as well as nanocomposites. So in this talk, I will just focus on the photocatalysis, and this was a very long journey. And I'm happy to see here in the session also Dr. Deborah Sarkar, which was took part in these studies along the years. So to put it in context, atomic and molecular layer deposition can be used in combinations to form organic, inorganic hybrid thin films, which in recent years has dramatically increased and drawn more and more research interest over the world. And this here you can see the increase. It is not up to date to recent years, but in recent years, actually there is a rapid increase in activity in this field. So this method allows. Okay, there is some terrible noise. If you could mute it. Is it possible to mute? Thank you. Atomic and molecular layer deposition allows a step-by-step deposition at the atomic and molecular levels, respectively, of thin films, while controlling the composition and details of the thin films deposited. Probably most of you has some background and aware, but I'll just give a very brief introduction. So this is a typical synthesis of aluminum oxide using atomic layer deposition by trimethyl aluminum and water. And the idea is that the surface is exposed sequentially to trimethyl aluminum, purged, so only one monolayer is reacted, then exposed again to water. The unreacted methyl groups are hydrolyzed, and at the end of this sequence, we have one monolayer of aluminum oxide. Now we can repeat this cycle, and by splitting the reactions between TMA and water to sequential reactions, we can grow the oxide film incrementally with atomic and molecular level precision. The field has evolved in recent years, as I mentioned, and nowadays, using molecular layer deposition and combinations with atomic layer deposition, one can synthesize thin films with well-defined composition and functionalities in a layer-by-layer fashion. And we utilize this in the context of photocatalysis, as I will show you soon. So the idea was, when we started this journey quite a bit long ago, was to take some substrate and deposit titanium dioxide on the substrate and then study the photocatalysis of these thin films. One may go with the approach of using atomic layer deposition using titanium tetrachloride and water and directly deposit titanium dioxide and study its properties. However, we decided to do the following thing. We decided not to use titanium tetrachloride and water, but rather use titanium tetrachloride and ethylene glycol. Therefore, this would be molecular layer deposition, where we deposit in a layer-by-layer fashion titanium ethylene glycol titanicone films. And this results in titanium ethylene glycol hybrid film, which is amorphous. It is a combination of oxide and organic components. And then apply in the middle some processing, I will show you soon, anneal the film and get the oxide. So for some reason, we chose to take the long way of attaining the oxide by making an intermediate organic inorganic hybrid film. The idea behind this was that having this hybrid film, which has the organic functionalities, would have a metastable or less stable properties compared to the pure oxide, which is a very stable material. And this will allow us to do all kinds of manipulations, as you can see here. For example, introduction of defects. The defects are very important in catalysis and in photocatalysis. So this way we can introduce it controllably. We can introduce doping. We can control the permeability because we start from an inorganic hybrid material, which could be permeable or non-permeable depending on the synthesis conditions, unlike pure oxide that is very difficult to manipulate. Band gap design, and also manipulate the stoichiometry of the final film. So this was the concept. And here is an example where we synthesize the thin titanium ethylene glycol hybrid film by molecular layer deposition. We incorporate metal ions, cations, and then anneal the material, and we get very controlled doping. As you can see here, this is the optical absorbance spectroscopy of such films, which are just a few nanometer thick. And you can see that we can incorporate almost any dopant very controllably and very easily into this material. And we take advantage of the fact that we first synthesize this amorphous titanium ethylene glycol hybrid film, which is permeable and can incorporate easily dopant atoms. And this was one of the first demonstrations of this methodology. Here you can see this is the step-by-step synthesis of the films, and you can recognize here the inorganic titanium oxide clusters linked here, you can see, with the organic components, which is overall a titanium ethylene glycol film. And by making this, repeating this over and over again, one can deposit this hybrid organic inorganic thin film with controlled thickness. And before it is annealed or during the anneal, one can manipulate and control all these important characteristics that I will show you that result in high performance titanium dioxide thin films with properties that are usually much more complicated or difficult to attain using other types of synthesis methods. Here, what you see are the anneal temperature, the calcination temperature applied to the thin films. And this is the activity toward two model reactions. One is the direct photocatalytic production of hydrogen peroxide. And you can see that depending on the calcination temperature, there is a peak at 520 degrees Celsius. And here what you can see is a model test reaction for decomposition, photodecomposition of benzoic acid, where there is a peak in the activity when the films are calcined in 650 degrees Celsius. All experiments were performed in room temperature, and the temperature specified here is only the anneal temperature applied before using the films. So you can see it has very interesting behaviors. And we started in a very long journey to study what are the mechanisms behind these activities. One should note at this point that typically titanium dioxide cannot efficiently produce hydrogen peroxide without using sacrificial compounds, and cannot totally decompose benzoic acid because of the thermodynamics of the system. And these films can do this. So we will see what's behind it. So we tested the photocatalytic activity of titanium ethylene glycol annealed at different temperature for different benzoic acids. And here you can see a comparison in the reactivity comparing titanium ethylene glycol, the Gusa nanoparticles, and pure TiO2. And you can see the lower the graph, it means the activity is much higher. So you can see that indeed these films annealed at 650 degrees Celsius are much more active than pure TiO2, but also much higher than the standard used, the Gusa nanoparticles. Here, what you see is the catalyst used for hydrogen peroxide. And this catalyst, the tubes that you see here, are the titanium ethylene glycol films annealed at 520 C. And inside you can see like P pods. These are gold clusters where gold is deposited both inside and outside. And by the synthesis conditions, we can control the distribution of size and also the distribution of inside versus outside decoration. And this is very important. Turns out it's very important for electron transfer here, which is required for the electron transfer in the reduction step. This is how it looks. We did a very thorough study where we studied the performance towards hydrogen peroxide production with anneal temperature of the catalyst and number of cycles, which means the thickness of these oxide tubes. And you can see that there is a very prominent activity peak at 520 degrees Celsius here. And also there is some threshold of thickness where activity begins, and you can see it here. This is how this cross-section looks. If we use a co-catalyst, for example, scandium, one can get relatively high hydrogen peroxide production, photocatalytic production, as you can see here. This is changes the kinetics of the catalytic reaction. And again, I want to stress that the hydrogen peroxide produced here involves no sacrificial compounds, and this is purely redox reactions of water and oxygen molecules dissolved. This is quite unique for titanium dioxide. And then the question came, what makes these unique reactivities? When we anneal at 650, how come it becomes this super photo catalyst for oxidative decomposition of organics here? And when we anneal it at 520, why do we get this unique photocatalytic reactivity towards hydrogen peroxide production? So what is special about these anneal conditions, and what is special about the material that we obtain? Simple elemental analysis showed that it has some carbon impurities. However, this oxide is not carbon doped titanium dioxide, and this was very interesting. So we did a quite thorough analysis combining different spectroscopies. One of them I show here, and we studied the band gap and band alignment evolution of the oxide with anneal temperature. And what we found out is that when we anneal this material at 650 degrees Celsius, both conduction band and valence band has a very significant downshift, specifically with the valence band downshift of 450 milli-electron volt, as you can see here. While when we anneal this or calcinate this material at 520 degrees Celsius, the shift is much more moderate, is 140 milli-electron volt. However, we obtain two new defect states that are located just between the Fermi level of gold and the conduction band of the oxide. Here you can see defect state 1 and defect state 2. And this actually gave some good explanations of both phenomena that we observed. And the first, the photodegradation of benzoic acid, became clear because now the photogenerated holes here in the valence band are much deeper, which means in redox terms that these holes are much better oxidants compared to standard valence band positioning. For the hydrogen peroxide production, it also made it clear because these defect states allow to mediate electron transfer from the photoexcited electrons from the conduction band to the gold Fermi level, and therefore override the kinetic barrier that usually hamper the efficient photocatalytic reaction of titanium dioxide by having these intermediate states that facilitate electron transfer of the photoexcited electrons. And by looking at the deviation from stoichiometry, delta, and the steady state level of hydrogen peroxide, you can see there is a very nice linear fit for all anneal temperatures that are represented here by the different stoichiometry deviations. However, for this 420 degrees Celsius, one can see that the data point exceeds by this much from the correlation, and one can ascribe this enhancement in the activity to the improved electron transfer rate of the photoexcited electrons to the gold Fermi level. So this gave us some nice understanding of the unique features that are obtained by controlling the processing temperature. But we still remain with a bit deeper question. So what is the mechanism resulting in deep valence band oxide? So one cannot explain the deepening of the valence band by defects, and because defects usually will destabilize the system, and this will make an upshift. And also doping is not appropriate for this. And this was something that we were quite convinced that is we have to explain also by looking at the fluorescence spectroscopy of terephthalic acid being decomposed by TiO2, which is conventional TiO2 here, and titanium ethylene glycol at 650 C. So what you can see here is expected that for TiO2, the more you shine UV light, you form more of the OH adduct of terephthalic acid, which fluoresce, and fluorescence increase until you get some steady state level, and that's it, because TiO2 would not decompose this molecule. However, when we do the same experiment with our films, we see a much sharper increase in the fluorescence, which means that we form much faster the OH radical adduct here. However, soon after, this decomposes and vanishes completely. So, and here on the right, what you see is a comparison of the rate constants and the shift in valence band that I just showed you here before. And there is actually nice correlation between the two. So it was clear that this downshift has some important thermodynamic and kinetic aspects that we wanted to further understand. And this was for a while a bit difficult to pinpoint, until at some point it became quite known that strain effects in oxide affect band gap and band position. And this is a reference to some of the papers that showed this very nicely, where inherent strain in the oxide can shift the band positions and also modulate band gap. So we decided, and Debu contributed significantly to this work. We decided to look into Raman data that we had, and Raman position of certain peaks of the oxide can assist in quantifying inherent strain in the oxide. And indeed, what we saw that for this activity region where anneal temperatures show increased activity, which correlate with the shifts also, indeed there is a Raman strain, what we call Raman strain. So from the Raman data, we could deduce that there is an inherent strain in the oxide. And this started quite a long journey where we not only looked on how better our films performed compared to others, but we decided to do a more systematic study and take substituted benzoic acid and study the kinetics and how those correlate with the electronic parameters like ionization potential, charge density, dipoles, and so on, and quantify all this. What you see here is correlation of the rate constants and the ionization potentials. You see correlate very nicely. And the electron density at the anchoring group, the dipole, and the charge. And all correlates very nicely. So it was clear that the rate constants correlate with the electronic features of these molecules. And then we also wanted to do some experiments where we do it in a solvent-free environment, meaning we take the photocatalytic films, we bind spectroscopic markers, which are porphyrins, and we study the degradation, as you can see here, by following spectroscopically the Soré band of these molecules as a function of irradiation time. And all of this is done with no solvent. So we can only quantify the pure electronic effects by varying the porphyrins. And we did it for 4 porphyrins with different substituents here. And then what we saw is very interesting, that unlike the single exponential kinetics, first order kinetics of benzoic acids, for porphyrins, we obtained two regimes, fast and slow regime. And you can see here that you have 2 regimes, and this is for each of the porphyrins. And here again, we looked into the electronic details of these molecules and how they correspond to their activities. Because of time, I will skip on and just summarize what we found. So we found the following. The strain induced or generated in the oxide when annealed at this elevated temperature and cool down result in shift of the valence band and conduction band, and this is what you can see here. So there is a shift, a downshift that is marked here, and this is the downshift that we found here. This downshift affects the thermodynamics of the system, because now when you photogenerate holes, these holes are much deeper with respect to the vacuum level, which means much more oxidative. So they can break up molecules that are very stable and usually cannot be broken up using such an oxide. However, you have to take into account additional effects, and these are the effects of the dipoles that form when you have a monolayer or a densely formed monolayer attached on the oxide surface, and this forms a shift of the work function. And for tightly packed monolayer, dipole monolayers, there is an upshift as a result of this packing, which cost you thermodynamically in lowering, again, canceling some of the downshift that you had because of the internal strain. And the reason that our films can still break up such molecules is because to begin with, we have an excess of almost half EV downshift. So this effect cancels out and you can still have enough oxidation potential for the photogenerated holes. The reason we have these 2 regimes is that is observed only for the porphyrin monolayers, is because as these photogenerated holes chew up and break up porphyrins, the dipole density goes down, and at some critical level, the work function changes abruptly, and this is a well-known phenomena of 2D dipoles on a solid surface. And this is the transition point that you can see here that correlates very nicely. Here you can see the transition point in coverage that correlates very nicely with the electron density at the anchoring group. So with this, I would like to summarize that this methodology that I showed you, relying on making metastable hybrid organic inorganic films, allows us to manipulate all of the relevant properties for photocatalysis and obtain these unique reactivities with a material that is considered well-studied and well-known. And I would like to thank the people that assisted and some funding. And I would like to mention Debu, that is here in the audience with us, which was took part in some of the research presented here. Thank you very much.
Thank you, Professor Wei. You are finished on time. So the session is open for the questions, queries. So there is one question in the chat box. The question is, do you find defect from measurement? How do you find the defect from measurements? Will it change the properties of the system?
Again?
Yeah, the question is, how do you find the defect from measurement? Will it change the properties of system?
Yes, so defects are very important for this for the performance of these materials. For example, if you look here, so this intermediate electronic states form because of defects, and they allow the fast electron transfer of photoexcited electrons to the gold nanoparticles, and therefore we can overcome the well-known kinetic barrier of reduction, oxygen reduction, that is typically hampering the whole hydrogen peroxide production. So of course, this is very important feature.
Yeah. So one more question I have. We have seen that TiO2 in presence of hydrogen when we anneal at a high temperature. So there are several changes in the energy levels, like conduction balance. So can you correlate your results with those in presence of some carrier gases like hydrogen, like reducing gases or inert gases?
Yeah. Okay. Very good question. So all the studies that I showed you here were done where these hybrid organic inorganic films were annealed under air or oxygen. So if you anneal this under hydrogen, because and the reason we do it is we have carbon in the system, and again we don't want to get necessarily carbon doped titania, and if you anneal it under hydrogen, you may get totally different material starting from this organic inorganic hybrid, and this is indeed very important parameter.
Thank you. And one more last question. So you mentioned that there is a abrupt change from the 520 to 650. So what happens when the temperature, annealing temperature increases to 700? Suddenly there is a large separation.
Right. Yeah. So as you can see here, shifting from 520 to 650, you get two effects. One is the downshift of the valence band, and another one is that these defects are unique just to 520. The reason it is unique to 520 is probably a combination of thermodynamic and kinetic effects that occur while you anneal this system. And on the one hand, you have the decomposition of the organic components, and on the other, you have concomitant crystallization of the oxide clusters. And at the end, there is some sweet point where you can retain structural defects that give rise to these states. When you go on and anneal it at higher temperatures, you increase the crystallinity of the system. I did not show, but the higher temperature, you get larger and more crystalline structure. But you also start at certain point to have phase transition from anatase to rutile, and all of this together changes the system again. So to get efficient photocatalysis in our system, which is quite different from other titanium dioxide systems, the optimum is to have it annealed at this region.
Thank you, Professor. Such a wonderful presentation. I will learn so many things from your presentation. Thank you. Thank you once again on behalf of the organizing committee.
Thank you very much.
Yeah. Now we move to the next part of this session. It's contributory lectures, and we have 3 lectures, contributory lectures, and I request the presenters to stick to the time. 10 minutes you have, and you have to talk up to 8 minutes, and 2 minutes are reserved for the question and answers. So now I request Ms. Richa Dubey to share her slides.
Sir, am I audible?
Please stick to the time.
Yes, sir. Sir, am I audible?
And make your audio a little loud because it is not audible.
Okay, okay, sir. Am I audible, sir? Hello? Sir, am I audible?
Ms. Richa, your voice is not.
A little more louder.
Ma'am, am I audible?
It's very feeble. Your voice is very feeble.
Am I audible?
Okay.
To some extent now.
Start.
Hello? Hello?
Yeah, please share your slides.
Sir, now I have shared my slide. Is it visible?
Not yet.
Hello?
Not yet. We can't see your slides.
Just a second, sir. Sir, I have shared my slides, sir.
No, we cannot see your slides.
Sir, might be somebody else is sharing because it is writing that one participant can share at a time.
No, nobody is sharing. Already Professor Robi has remote is sharing.
Okay, I'll try once again, sir. Sir, now is it visible?
No.
Sir, I'll try once again.
Just try to refresh your system. Richa,
Yes, ma'am?
try to refresh your system and then share.
Yes, ma'am. I'll try.
We'll try the another one. Ms. Abhirami Mutumani.
Yes, sir.
Yeah. Are you ready?
Yes, sir. I'm ready.
Yeah. Please share your slides.
Okay, sir. Okay.
Then we'll go back to the Richa, Miss Richa.
1 second, sir.
Yeah. Okay. Meenal.
Sir, screen is audible, sir? Hello.
Please go ahead.
Sir, is audible, sir, my screen?
Yeah.
Okay, can I start, sir?
Yeah, please.
Good evening to all. I'm Ms. Ambirami, research scholar from the Department of Chemistry, doing research work on electrochemistry under the guidance of Dr. M. Sivhami. My topic for this presentation is synthesis and characterization of bismuth oxide nanoparticle using plant extract. An outline of the presentation is introduction about the nanoparticle and the benefits of using the plant extract, materials and methods used for the synthesis and the characterization studies under the resultant discussions. And finally, the conclusion. At the introduction, nanotechnology has gained a huge attention on the past decades. The fundamental of the component of nanotechnology is the nanomaterials, and the nanoparticles. And the nanoparticles are the particles size between the 1 to 100 nanometer range. It will be made up of carbon, metal, and metal oxides and organic matter. It have the different shape, size, and the structure. The surface can be uniform or irregular with the surface variations. In the nanoparticle synthesis can be developed by various methods like physical and chemical methods. Is based on the properties and the reduce the production cost. In nowadays, we need to develop the eco-friendly processes which do not use the toxic chemicals in the synthesis protocols. Here we used as a biosynthesis. In the biosynthesis, we take as a plant parts like stem and leaf, flowers, and the root of the plant parts. Here we take as a plant leaf for the plant leaf extracts are believed to act as a both reducing and stabilizing agent in the nanoparticle synthesis. It
Abhinami,
also, ma'am.
can you zoom? It's not seen, it's not visible. Your presentation, can you zoom it?
Is it okay, ma'am?
Yeah, ma'am, proceed. Thank you.
In the plant leaf extracts are act as a both reducing and reducing agent and the stabilizing agent. It's also act as a capping agent to prevent the agglomeration of the nanoparticles. Here we synthesize the bismuth oxide nanoparticles. Why we take this as bismuth oxide means it is a famous semiconductors in the last recent years. It will be used as a lot of the field such as gas sensor, fuel cells, optical coating, supercapacitors, etc. In this work, we have synthesized bismuth oxide nanoparticles by using the cardiospermum helicobacter plant extract, and the characterization studies can be done by this presentation. And then materials and methods. Preparation of the plant extract. The fresh leaves of cardiospermum in the Tamil name is Mudakathan. It will be collected under the gardens near to the garden, and it will be washed for distilled water and dried at the room temperature for the few days, and it's grinded into the fine powder. This powder is dissolved in the ethanol, and the extract is made by the Soxhlet apparatus for the 9 hours, and it will be filtered by the Wattman filter paper, and then plant extract will be obtained, and it is used for the further studies. Here we take as a precursor materials of bismuth oxide, synthesis of bismuth oxide nanoparticle is a bismuth nitrate pentahydrate, and the molar ratio is 0.1 mole. In that, we take as a different molar ratio by adding the plant extract. We take as a 10 ml, 20 ml, and 30 ml of the plant extract by calculating of the 100 ml. If, for example, if we take as a 10 ml of plant extract, we add a bismuth nitrate precursor for the 90 ml. For the three different solution, we made like this, and this after adding of the plant extract, it have stirred for the 4 hours, and then it will be centrifuged and get the precipitate that will be dried at the oven for 60 degrees Celsius, and then we get your bismuth oxide. And then characterization we done as a UV visible spectrum with a band gap and FESM images, and with a EDAX and dynamic light scattering and the fluorescent spectrum. Resultant discussion and UV visible spectrum with the band gap. The absorption wavelength range of the bismuth oxide is 230 to 400 nanometers. We get the sample first. We get the wavelength of 265.76 nanometer with a band gap of 3.5 electron volt. And then second sample, we get the 291.80 nanometer range with the band gap of 2.13 electron volt. And the sample 3, 278.01 nanometer range with the band gap 2.8 electron volt. In this first sample has the band gap is high because of the particle size will be increases for the particle size will be increases for the when a temperature it will be high. Temperature it will be high means the band gap will be increases. Then semi images of bismuth oxide and the EDAX images. Here the first sample we get the sheet like structure, and this and here the bismuth peak is high due to the formations of different phases. In bismuth oxide have the 5 different polymers like alpha, beta, gamma, delta, and omega. In this we get different phases, and then 20 ml of the sample we take as it like some spherical like structures. Under the third sample we get some agglomeration which will be some agglomeration will be obtained in the sample 3. In this 3 sample bismuth and the oxygen value is it's near like the same, and bismuth value is high. In this we confirm the bismuth oxide can be formed. And the DLS of the bismuth oxide, dynamic light scattering.
You have
So,
only 2 minutes.
okay, sir. Let me finish. In the DLS spectrum, we can conclude the particle size of the particle size of the sample. We get in this three sample, we get the particle size. It may be 150 to 160 nanometer range. And then the fluorescence spectrum. In the fluorescence spectrum, in the nanometer range is 656.39 nanometer in that whole 3 samples. And the conclusions in this in this work we synthesize the nanoparticle by using the plant extract as a reducing agent, and the characterization can be done by SEM and UV visible spectroscopy, and the particle size was estimated around 150 to 160 nanometer range. In this plant method of synthesis, metal oxide nanoparticles offers an efficient, economic, and eco-friendly approach that does not need any special conditions such as vacuum condition, catalyst, and sophisticated instrument. These are the reference for this paper. And thank you for all kind attention. Thank you.
Thank you, Abhinami.
Thank you, sir.
One question from the audience. Okay, then we move to the next speaker, Richa.
Yes, sir. Shall I share again, sir?
Yeah, please.
Yes, sir. Sir, I'm not able to share my screen. I don't know why. Every time it is failing. Hello?
Not able to share. You can send by email. What is the problem, Richa?
Sir, it is just showing you're not able to share the screen. That's it.
You're logging in through your mobile?
No, ma'am. I'm using my laptop, ma'am. Ma'am, some error code sharing screen has failed to start. Please try again later. That's all what I'm getting, ma'am.
1 second.
Yes, ma'am. I'll try to share again, ma'am.
Yes, actually you are logged in through 2 systems, so that's why there is a problem, I guess. Try it again.
Yes, ma'am. Ma'am, I'll try.
Oh. No, actually दोन्ही system में तुला co-host केलं.
Ma'am, is it? No, ma'am. Every time there is an error code, ma'am.
Can you send it by mail?
Yes, ma'am. Yes, ma'am. Ma'am, should I send on the same icon link, mail ID, ma'am?
Yeah, which mail ID are you?
Ma'am, that ICONN-21 we are getting regular.
No.
You see the chat box. Now we can see.
Now
your
we can
phone.
see your screen.
Yeah, we can see. Your
Yes, ma'am.
screen.
Yes, ma'am. Yes, ma'am.
Yeah, you start, please.
Okay,
You have 8 plus 2 minutes. Okay.
Yes, sir.
8 plus 2 minutes.
Yes, sir. Sir, am I audible?
Yeah, please start.
Yes, sir.
Can you make your
I am
phone
Richa.
horizontal? Your slides are not visible properly.
Okay.
You are doing on phone. Why not? You have laptop visible, right?
Actually, no. Sir, I have opened my laptop parallelly, but I wasn't able to share on my laptop.
Okay.
So
Okay.
I started with my phone. Yes, sir. Hello.
Put it horizontally, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am. Now is it okay, ma'am?
Yes, this is fine. Continue.
Okay. So I am Richa in the School of Electronics Engineering from VIT Chennai campus. I'll be presenting my research on data-driven evaluation for the physiochemical performance prediction of heteroatom doped biomass derived
Richa, there is a problem in the audio. We cannot hear anything. Hello? She is not in the meeting.
Yes, just hurry up, Richa. Yes, are you? Yes, hurry up. Yes, Richa, are you going to present?
Yes, ma'am. Hello.
No, we're just waiting for you.
Yes, ma'am.
See, if you cannot share, at least just tell your work.
Yes, ma'am. Actually, I'm not able to share, ma'am. I'm facing some issues, ma'am. Wait, just
Don't
2
worry.
seconds.
Don't worry. Just
Yes,
tell
ma'am.
what is
Yes,
what are the aim and
yes, ma'am.
your objective. Make it short.
How are you?
Ma'am, is it visible now?
Yeah, it's visible.
Yes, ma'am. Shall I start, ma'am?
Please.
Please, you just go to your results.
Yes, ma'am. Yes,
Okay,
ma'am. Yes, ma'am.
Make it horizontal and start.
Yes, ma'am. Yes, ma'am. Actually, I was talking of the need for the green energy-based electrode materials. So as we can see, for the energy consumption, it is giving rise to the energy demands as well as the environmental pollution. So we have to switch on to some green solution, and for that, biomass-derived carbon electrode materials inhibiting ordered hierarchical biological surface chemistry could be a good choice. So looking, a lot of numerical researches have been based on these biomass materials, but still to date, no
Just
computational
go to your
analysis.
results.
Okay, ma'am. Research methodology, ma'am. Shall I discuss my research pathway?
You just go to your results.
Okay. Okay. So for my analysis, for the computational analysis, I have taken total 300 biomass-derived carbon samples, and I have selected total 10 parameters on which are going to affect the specific capacitance as well as the energy density of the biomass-derived materials. So for the parameters, I have considered the surface area, total pore volume, pore size, micro pore volume, meso pore volume, the intensity of D by G ratio, internal resistance, nitrogen percentage. So as we can see, there are various reasons associated with the selection of parameters. For example, the micropore helps in the formation of double layer, whereas the mesopore helps in the ion transport channel. So we have considered these two parameter volumes separately, and aspect ratio and cellulose content are the unique features of the biomass derived species. So for the dimension differences and acceleration conversion efficiency, first we have normalized all the values, and the different parameters selected along with the minimum, maximum, mean, and standard deviation values are tabulated in table 1, whereas table 2 provides the different configuration setup for ANN as well as machine learning methods that I'm going to share next. So first, we have considered the different performance parameters which are going to affect the specific capacitance. We found that there was no direct relation between the different parameters along with the capacitances. So we have designed an ANN model consisting of 20 hidden layers, 10 input layers, and one output layer. And for the ML methods, we have considered 5 ML methods, that is the multi-layer perceptron, linear regression, support vector regression, random forest, random tree, and ANN model. So as far as the results are considered, we can see for all the different models that we have suggested, the training, validation, test, and ANN model for ANN was giving the correlation coefficient value as 0.99, which is approximated as 1. And we can see most of the data are quietly fitting the expected as well as the predicted values. And for the quantification assessment, we have taken 5 different error performance parameters, and their values was calculated for different ML methods. That is, MLP was having correlation coefficient value of 0.85 and so on. So 5 performance parameters that we considered was correlation coefficient, mean absolute error, root mean square error, relative absolute error, and root relative square error. So table 3 tabulates the values of these error performance parameters based on the different ML methods. From table 3, we can see that random tree and random forest are having the maximum correlation coefficient, whereas the root mean square values for these two methods were relatively low. Hence, they were able to predict the capacitances very easily, or we can say more accurately as compared to the rest other parameters. After getting the prediction of capacitance, we move for the prediction of energy density. Again, we considered our design NN model as well as the different ML methods, and we found that for the training, validation, test, and overall samples, the value of correlation coefficient was 0.99, which was again which was providing a very good fit of the experiment as well as the predicted values. And we have tabulated the error performance parameters. Again, we found that the values of correlation coefficient for random tree and random forest was very high. That was nearly equals to 1. And the root mean square values for those two methods was really very low. After that, we went for the scan rate evaluation or variation along with the specific capacitances. We found that it was in very good agreement with the specific capacitances, and we further moved for the experimental power density with the variation of the nitrogen content. For example, we considered the different percentages of nitrogen which are used in the literature, and then we found, as is evident from the pie chart, the different parameters show different contribution to the overall specific capacitance of the value. Three parameters are having the major role, that is the total surface area, the internal resistance, and the total pore volume, whereas in comparison to these three, nitrogen percentage was having a less significant role. So my concluding remarks, we have considered total 300 samples of biomass carbon electrode. We have trained it using ANN model. And for the ANN, we have used the Levenberg-Marquardt backpropagation algorithm. And based on the error performance parameters, all these 6 models can be arranged in following order. ANN was showing the best result in compared to RT and RF, and the linear regression was showing the least correlation values. And so out of all these, we found that surface area, internal resistance, and total pore volume of the carbon-based, biomass-based carbon electrode materials are they play a major role considered or we can say in respective of all other parameters, they were having more significant importance. So the challenges in future perspective, biomass generally has irregular morphology, so the pore geometries like shape and structure are difficult to tune precisely, which limits their rate, performance, and power density. So for investigation of the diffusion process of ions in hierarchical pore structure is still a challenging task. So for addressing these issues, there are few directions which we propose. For example, developing proper theoretical models along with ML methods. Second, more research on heteroatom-rich biomass-derived electrodes. And third, application of different training functions. For example, Bayesian regularization, backpropagation, etc. These are my references. Thank you.
Yeah, thank you, Ms. Richa. Is there any
Thank you, sir.
question? Okay, there are no more questions. So, is there Mr. Sanjeev Baglari? Mr. Sanjeev, are you there?
No, sir, I think he's not there.
Yeah, I think this ends session here. Thank you very much, all audience for attending this session. And I just transfer this to the organizing committee. Thank you very much.
Thank you, Balchandra sir, for chairing the session, and I thank all the participants for having participated. Thank you. Thank you. The session ends here. Thank you. Have a nice day. I think we can leave.